All right, hello. Uh, in the first half of the video, I will talk about 3D space, 3D space, and then in the second half of the second video, I will talk about distance in 3D space, okay? So before I do that, let me just do a little introduction or continue on the introduction that I had earlier. So we had the set of real numbers. This is a set that contains all repeating decimals and all non-repeating, non-terminating. This is a set of all repeating decimals, terminating decimals. This is x, such that x is terminating decimal, or repeating decimal, or non-repeating and non-terminating decimal. Let me just give you a quick example of what I mean. So a terminating decimal is something that looks like 2.7 or 2.71. A repeating decimal is something like 6.5424242. That's a repeating decimal. We can change this to a fraction of two integers. We can change this to a fraction of integers. Okay? So these are rational numbers. Okay? Non-terminating, non-repeating decimal, this guy, we can write it as, I don't know, the pi is one of those. The square root of 2 is another one. Okay, those are irrational numbers. And I can craft one example that looks like, that has a pattern. Okay, this is non-repeating, non-terminating decimal. It doesn't stop, and it's not really repeating. It has a pattern. So these are irrational numbers, okay? So the series of real numbers contains all of these. And as it turns out, okay, as it turns out, the set R and the set of points on a line are in a one-to-one correspondence. Enough points and enough numbers, they are in a one-to-one correspondence, okay? Exactly the same number of elements in the set of natural numbers, I mean in the real numbers, as well as the number of points on a line, okay? R is in a one-to-one correspondence with the set of points in a line, or I'm not sure if I should say on a line. Okay, what that means is this. Say you take a line, so you have a line, and it's not a line segment, so it's not stopping. Okay, this line is crooked. Let me change. Let me make another one. So I'll start here. Okay. So the points in this line and all of these numbers combined, all of these repeating, terminating, non-repeating, non-terminating, all of them put together, they have exactly the same one-to-one correspondence. Exactly one number for each point and 1 point for each number. So how do we do that? We pick a point and we just simply pick an origin. And then we pick a random point and say, okay, this is where we place 1. That's just more like a yardstick. And then every point, we can measure the distance from 0 and we can give it that name. For example, this point here is 3 units out from the origin. and therefore that represents the number 3. This point here is -2. Also, if I give you a point, say 2.7, then you measure 2.7 units from the origin, a directed distance. Okay, so that means because 2.7 is positive in this direction, you measure 2 units in 7/10 of a unit, and you place that 2.7. Every point has a real line, a real number, and every real number, a name, a real number, and every real number has a point. So that's the one-to-one correspondence. And hence we create a number line. We blur the difference between point and number, because each number has a point and each point has a name, a real number. We call it a real number line. Okay, we create the number line. Now, this is 1D, one-dimensional line. We can now move up to a two-dimensional line. Okay, we can move up to 2D by creating on the plane 2 lines. We create 2 lines on the plane conventionally but conveniently perpendicular lines. Okay, conveniently, I'll tell you the convenience here. Okay, and we call this the x-axis, the first component axis, and this the y-axis. Okay, the second component, that's the first component, and that's the second component. Okay, so in the clockwise direction, from the first component to the second component will give you the positive sides, kind of like the right hand rule. From x towards 90 degrees in the counterclockwise direction, you get the positive side of the y-axis. Okay, that's also another convention. Now, to place the point 2, 3, we measure 2 units. So we have to have a yardstick here and another yardstick here for the y-axis. Then to place the point 2, we measure 2 units on the x-axis, and we measure 3 units on the y-axis, and we get 2, 3. So you know this point now has a name. The name is the order pair 2, 3. So every point on the plane has an ordered pair, and every ordered pair represents a point on the plane. Okay, what does this really mean? This means that the point is 2 units out from the y-axis. If you measure it from the y-axis, it's 2 units out from the y-axis. Okay, so that's basically what that is. So this is a point on the plane, whereas this is an ordered pair. Now, again, we blur the names, and then we say, oh, this point is the point 2, 3, when it's supposed to be the point, and its corresponding ordered pair is the number 2, the ordered pair 2, 3. This is what we call a rectangular coordinate system. We could have used 2 lines, one going this way, one going that way, not necessarily perpendicular. Okay, we could have used x and y. They're not necessarily perpendicular, but if that is the case, so if you want to do the 1 by 1 by 1 rectangle, you're going to measure 1 unit here, 1 unit here, and it will never look like a rectangle. So conveniently, we pick the right angle axis. The 2 axes make a right angle, and not really an oblique angle like that one. Okay, that's why we have a rectangular coordinate system. Okay, it's a convention and it's very convenient. Imagine creating this circle x squared plus y squared equals 1 on the xy plane, where if the plane axis would look like this, it would be an oval instead of a circle. Okay, now going to a 3D space. So if we go to a 3D space, that means a 3D space in 3D. Let me first create a box just to give you a 3D idea. Okay, I'm gonna draw a box. So here I have just a box, and it's a rectangular, meaning things are all perpendicular to each other. So we can see that these two lines are perpendicular. These two lines are perpendicular. Also, we can see that this line, this vertical line here, is perpendicular to that plane, at the bottom plane. In other words, if you pick any line passing through this point on the plane, it's perpendicular to it. Particularly, it's perpendicular to this edge, and it's also perpendicular to this edge. Okay, so in 3D space, this point here, we can measure its distance from the bottom face by measuring this distance. We can also measure this distance, the distance from the opposite face, by measuring that distance. Or we can also measure its distance from the side face by measuring this distance. Okay, that distance from the opposite face, and this distance, vertical line. And so on a space, we now can put 3 lines perpendicular to each other and create a 3D axis. And to do that, here's what we do. We get the x-axis. So we have, for this plane should have, the bottom plane should have an x and y axis because it's a plane. Okay, so I'm going to make an x and y axis. So that may be my x-axis, and this may be my y-axis. So I have a plane, and then the z-axis will go up perpendicular to the two. So how do I decide which one is a positive side of the x-axis? Okay, so this is going to be my 1 unit, 2, 3, 1, 2, 3 on this is the x-axis, this is the y-axis, and this is the z-axis. So basically, in my graph, in my picture, this could be the x-axis, this could be the y-axis, and this could be the z-axis. And here's the convention. The convention is that x and y axis are perpendicular to each other. Okay? That x and z axis are perpendicular, and that z and y axis are perpendicular. Okay? That's one convention. So we can have a rectangular system. The second convention is, if I wrap my arm, my hand around from x to y, from the positive side to the y-axis, to the positive side of the y-axis, my thumb should be pointing to the positive side of the z-axis. Okay? So let me show you what I pulled out from the book. So from x to y, if I rotate my finger, my thumb should point to the z-axis. Okay? So the z-axis is not down like so, but it's up like up like so, because x is this and y is this. Had I chose to have x and y, oh no, had I picked x and y, then I would have to go from x, my arm will turn around from positive x to positive y, and my thumb will point down. So the z-axis would count down, the positive side of the z-axis. That's the right-hand rule, okay? So we apply the right-hand rule in creating our x, y, and z. So the right-hand rule. If you're familiar with screws, okay? If you're familiar with screws, and if you turn the screw from x to y, it will go up towards the z-axis. If you turn the screw from x to y, it will go up, screwing up to the z-axis. If you're familiar with the right-hand screw. Okay, there are some left-hand screws for some reason, for a specific reason, but in general, we always have 99.99% of the time, our screws are from x to y and then towards z. Now, so here is my 1 unit, 2 units, 3 units, 1, 2, 3, 1, 2, 3. Okay, say I want to put 2, 3, 5 on my space. So I measure 2 units on the x-axis, and that's where that should be, and 3 units on the y-axis. And now I'm going to make a segment parallel to this, passing through that point. Okay, parallel to the x-axis, passing through a point 3, and I make another one parallel to this, passing through this point. And that point here, if I were to flip the page, the bottom page, like this face, and look at it from perpendicular point of view, this would have been 2 units and 3 units here, just like the XY plane. So that's what I have now. So this point here, let me fix that, is 3 units out from the x-axis and 2 units out from the y-axis, because it's the point 2, 3. But on the z-axis, okay, on the z-axis, I'm going to go 5 units up. So I have 1, 2, 3, 4, 5. Am I going to go that much from here? Not exactly, because, not exactly, because this is not 5 units, it's more than 5 units. So there's 2 ways I can place that point. I can start measuring from this point, okay, knowing that this is my yardstick, measure 5 units like so, okay? So I can do 1, 2, 3, 4, 5, okay? And place that point. That's like 5 units from the XY plane. So this point is 2, 3, 5. So if I made the box, let me see if I can pick a brown color and see if I can make the box. Okay, 5 units up, 5 units up, so this is a 3D box with 2 units, 3 units, 2 units here, 3 units, and 5 units high. Okay, So that point is 2 units out from, no, 2 units out from the YZ plane, from this plane, okay? 3 units out from the XZ plane, and 5 units up from the XY plane. Okay, so that's the rectangular coordinate system. In 3D, three-dimensional rectangular coordinate system. Okay. So let's see if I can show you what we have with the right hand rule. So that's the x-axis. From the x-axis, the fingers are going to the positive side of the y-axis, and then the thumb is going to the z-axis. Okay, that's what the positive z-axis should be. Now, the units on the x-axis, the units on the y-axis, the tick points on the y-axis, and the tick points on the z-axis, the positive points are like so. Okay. Let me see if I can put one more picture that I downloaded from your book. Okay, so let's put it here. I hope you can see it. So the bottom plane is the XY plane. The side plane here is the XZ plane. Okay, and the side plane here is the YZ plane. It's the YZ plane. Okay, and the positive X measures this way, negative X measures that way. And we don't usually put the negative side of the x-axis in the picture unless we need to place a point with the negative x component, because it makes it crowded, not because it's incorrect. Okay, the negative x. And the positive y-axis counts that way, the negative counts in the opposite direction. The positive z-axis counts that way, the negative counts in the opposite direction. Okay, so these are the coordinates that we have, rectangular coordinates. We do have other kinds of coordinates, polar coordinates and cylindrical coordinates, and we'll talk about them when we get there. Okay, let me see if I can put in one more picture that I downloaded from here. Let's see what this is. Oh, this is the same picture. Okay, it's the same picture, and this is a nice picture that I found in your book. Very informative. So the point ABC is A units out from the origin on the x-axis, B units out from the origin on the y-axis. That's the same as that one. Okay, so B units out on the y-axis, and C units up from the bottom, from the plane. In other words, C units up. Okay, so if I were to draw that and draw that, then I make a rectangle, because this is perpendicular. It's our perspective that doesn't make it look like, it doesn't look like a perpendicular plane, box or rectangle. Okay, so that's what we see here. I'm going to erase it, and then so you can take a look at it. So this is A on the x-axis, this is B on the y-axis, and this is point C on the z-axis. And I'm imagining that this and this are parallel. Okay, so that's what we have here with the XYZ axis. Okay, now to see some, so let's see if I have one more picture. That's the one more picture that I like to see. That's what I was referring to. Okay, so this point is the point A, B, C. So what would be this point? This point would be A, 0, 0. A on the x-axis, 0 on the y-axis, 0 on the z-axis. Okay, no movement on the y-axis and on the z-axis. This point is 0, B, 0. This point is 0, 0, C. So this point is AB, 0, third component. It's on the xy plane. That's why the third component is 0. And this one is on the xz plane, so the y component is 0. And this one is on the yz plane, so the x component is 0. Okay? So that's what the ABC point looks like. Now, let me see, let me go back to a two-dimensional space and do something that you're familiar with, okay? So in 2D, let's see if we can draw the graph of y equals 3. Okay, let's see if we can draw the graph of y equals 3, the constant function y equals 3. Well, here's your y-axis, here's your x-axis. So y equals 3 is the line that goes through the point 3. It's this line. This line is the line y equals 3. Why is that? This is the x-axis. That's the y-axis. This is the point 3. This is 1, 2. Why is it a horizontal line? Well, why it is because it's telling me that the points on this line, on this equation, are the points with the y component 3. I don't care about the x component. The y component has to be 3. So pick any point. Pick any point whose second component is 3. It's on the line. I don't care about the first component. That's what this is saying. I don't care about the x component, but I am forcing you to pick 3 for the y component. So every point on this line has their y component equal 3. So that's that horizontal line. What if I want to draw the graph of x equals minus 1? Oh, that's a vertical line. What kind of vertical line is it? It's the line passing through negative 1 on the x-axis. Okay? And all the y components are, all the x components are negative 1. Okay, negative 1 and whatever the y component is. Negative 1, whatever the y. It doesn't matter what y component is. All x components have to be negative 1. That's what this equation is telling me. So if when I'm drawing that line, I'll be drawing a vertical line. Okay? Now, similarly, in 3D, if you want to draw the graph of y, z equals 3, what does that mean? This means that any x, any y, and 3 on the z component. So let's see if we can draw that. Okay, I'm going to bring in that xyz axis that I stole from the book. Okay, and see if I can draw z equals 3. Well, z equals 3 is, let me change pencil. 1, 2, 3. So I'm going to draw any x, any y, but the z component has to be 3. So every point in this line, this much up, 3 units up, okay, on the xz plane, or any point on the yz plane, 3 units up, or anywhere in this plane. Is this plane here, parallel to this plane, parallel to the xy plane, but hovering up 3 units. is the graph of the plane z equals 3. Okay, we can do the same with the, I don't know, y equals 2. Let's do, see if I can draw the graph of y equals 2 on the xyz plane. Okay, so let's create an xyz plane, surface, I mean xyz surface space. This is the x, that's the y, and that's the z. Okay, let's do 1, 2. All right. It's a plane that's actually, in this case, sort of vertical plane. Okay, and it's 2 units out from the xz plane, parallel to the xz plane. So that's the y equals 2 plane. Okay, and so this is really similar to our system of what we had with 2D. When we say x equals -1, we really mean -1 unit away from the y-axis, parallel to the y-axis. And when we say x equals 3, y equals 3, we mean, oh, okay, the line 3 units away from the x-axis, but parallel to it. Okay, just like that here, z equals 3 is the plane that's parallel to the xy plane, and 3 units up. Okay, so that is our plane on 3D. These are just simpler equations. We'll work with other plane equations. Okay, we'll work with other plane equations. Let me do then one more example and stop the video so we can do the next on a different video. Okay, I'm going to do x squared plus y squared equals 1 on 2D. Okay, this is the circle of radius 1 on 2D. This is just the unit circle, radius 1, centered at the origin. Okay, so that's just the circle. This is circle of radius 1 units on the xy plane, the unit circle. Okay, what if I have this equation, x squared plus y squared equals 1 in 3D? Well, this is saying that the square of x and the square of y should add up to 1, but we don't care about what z is. That's what it means. We're not concerned about the z, but the x and y components should be, so that x squared plus y squared is 1. For example, 1 over square root of 2, comma 1 over square root of 2, and 5 is in this line, in this satisfies this equation. Okay, or 1 comma 0 comma, I don't know, -2, because 1 squared plus 0 squared is 1. I don't care about the z component. The x component and y component should add up, the squares should add up to 1. So how do I draw this? Let me make an xyz plane first, space first, x, y, z, and it looks like if I have only xy plane, I would have had a circle of radius 1. Doesn't look like a circle. All right, but it's telling me that, oh, okay, the z component doesn't matter. So the circle could have been here. It could have been here. It could have been here. So what we're making is a cylinder. Okay, this is a cylinder with radius 1 and right circular cylinder. Of radius 1 center, and the center axis being the z-axis. Okay, the center axis being the z-axis. All right, so this is just an intro on the 3D XYZ axis, and I will continue with distance in the next video.